We've seen how we can use definite integrals to find areas. Now we're going to use definite integrals to find areas, but our functions are going to be a little more complex. So let's start with this. Find the area under the graph of y equals f of x from -4 to 5, where f of x equals 9 for x less than 3, and f of x equals x squared for x greater than or equal to 3. You might remember that this is called a piecewise function, which means that it's a function made up of pieces of two other functions. So let's think about what a graph of this piecewise function would look like. If we were graphing the top part of this, y equals 9, we would have a horizontal line that goes through 9 on the y-axis. And the other part of our function, y equals x squared, would look like this parabola. So how can we deal with that? Well, let's look at y equals 9, and then only graph the part of that that has x coordinates less than 3. And we'll look at the graph of y equals x squared, but only keep the part of that graph that has y coordinates that are bigger than or equal to 3. So now we've got a graph that looks like this, but we have two more bounds that we need to look at. The x-axis also serves as a bound. So this is the region that we're trying to find the area of. Because our graph is made up of parts of two functions, we're going to find the area in two pieces. So we'll start with this piece, which is the part that's underneath the graph of y equals 9. To find its area, we'll integrate that function, 9, from -4 to 3, because the x-coordinates of the points in that orange area run from -4 to 3. The other part, the yellow part, is underneath the curve y equals x squared, and the x-coordinates in that part of the graph range from 3 to 5. So let's find these two integrals so that we can find the two areas. We'll find the antiderivative of 9, which is 9x, and then we'll evaluate that at 3 and at -4, and subtract those two values to get 63. So the area of the orange part of the graph is 63 square units. For the yellow part, we'll integrate from 3 to 5, x squared dx, because that part of the graph is underneath the curve y equals x squared. The antiderivative is x to the third over 3, which we'll evaluate at 5 and at 3, and then subtract those two values to get an area of 98/3 or 32 2/3 square units. Now we want the total area, so we'll have to add those values together to get an area of the entire region of 95 2/3 square units. Now let's revisit an idea from before, which is that area above the axis has a positive value and area below the x-axis has a negative value. We use that to look at graphs like these, where we said that the first graph would have to have a total area that's positive because more area was above the x-axis than below. The second one would have a total area that's negative because there's more area below the x-axis than above. And the third graph would have an area of 0 because there's equal areas above and below the x-axis. Now, saying that the areas of these graphs are positive or negative or 0 is really a little misleading, because what's positive or negative or 0 is really the value of the integrals that you see underneath each graph. The area in each case would have to be something positive. After all, we measure area in positive units. So if we're going to really measure the area that we see, we're going to have to find a way to compensate for the area that is negative and not look at it as negative area. Now, the integral that we were using to define the area underneath this graph from x equals -2 to x equals +2 was a single integral, and that was why we said that the area was kind of a combination of this positive part and this negative part. What we really need to do is figure out where the part of the graph that's above the x-axis and the part that's below the x-axis separates. So in this case, we need to find that x-intercept. Let's remember how to find the x-intercepts of a function. To find x-intercepts, we set y equal to 0. So we set the function equal to 0 and solve for x. When we do that, we find two x-intercepts, x equals -3 and x equals 1. And that's exactly what it looks like in our graph. Now the number that we're really interested here is the x equals 1, because that's the place where the positive part of the graph and the negative part of the graph are divided. And that also is going to give us some new values for our limits of integration, because the part above the x-axis has x-coordinates that range from -2 to 1, where 1 is that x-intercept. And the part below the x-axis has x-intercepts that range from 1 to 2. So if we take a look at those two parts of the graph and find their areas separately, then we can put those areas together and get the true area of the graph. So let's start by finding the area above the x-axis. For that part of the graph, our x-coordinates were between -2 and 1. So if we integrate from -2 to 1 our function, and then evaluate at 1 and at -2, and subtract those two values, we'll find that the area above the x-axis is 9 square units. The area below the x-axis is the same integral, but now we're going to evaluate that integral from 1 to 2. Now when we do that, we're going to get a result that isn't altogether surprising. We get a negative value, but we said that the area below the x-axis would be a negative number. To find the total area above and below the x-axis, we're going to have to take the absolute value of that area below the x-axis. So we'll consider the area below the x-axis to be a positive 2 1/3, which, when we add that to the 9, gives a total area of 11 1/3 square units. What if we're trying to find an area like this? This is an area between two functions, between f of x and g of x. It's still bounded by some vertical lines on the left and right, x equals a and x equals b, but in this case we're not looking for area that is below a function down to the x-axis or above a function up to the x-axis. We're between these two functions. If we integrated f of x from a to b, we'd be looking for this area. That's the area below the function f of x down to the x-axis. And that's way more area than we're looking for. And if we integrated g of x from a to b, we'd get this area, which isn't really the area we're looking for. It's below the area we're looking for. But what if we put those two ideas together? And we integrated from a to b f of x, which gives us more area than we want. But then we subtracted from that the integral of g of x, which in essence takes away the part of the area that we don't want. So if we want to find the area between two curves, we can do that by subtracting one of our functions from the other. The important thing is we're always going to have to know which is the top function and which is the bottom function, because in order to find the area between two curves, we have to subtract the bottom from the top in order to find the area in between once we integrate. So let's see how that works with this problem. Find the area of the region bounded by the graphs of y equals 2x plus 1 and y equals x squared plus 1. Well, let's figure out where the graphs intersect first. To do that, we'll set the two equations equal to each other and solve for x. And we find that there's two places where these graphs intersect, where x is 0 and when x is 2. So which graph is on top? Well, we know that in between 0 and 2, one of those graphs has to be up on top. So let's just pick a number in between 0 and 2, like 1. Substitute that x value in each equation and see what the y value is. So in the equation for the line, y equals 2x plus 1, when x is 1, y is 3. So 1, 3 is a point on the line. And when x is 1 in the parabola, y is 2. So 1, 2 is a point on the parabola. 1, 3 is above 1, 2. So the line must be the top function. So now we'll set up our integral. We know that the two functions intersect at 0 and 2. There's a region in between 0 and 2 that's bounded, and the top function in that bounded region is the line. So we'll put that function first, and then we'll subtract the parabola from it because that's the lower function. Now we'll do a little bit of algebra before we integrate, so we'll simplify and combine like terms. Then we'll find the antiderivative. We'll integrate from 0 to 2, and we get a value of 4/3. So there's 4/3 square units that are bounded by these two graphs. Now, was that a little tricky without actually seeing the graph first? Well, maybe it was. So let's think about it. There's no reason why you couldn't make a graph of the function before you try to figure out where they intersect. And if you do that, you would have had a picture that looks like this. You can see from the graph that the two x values where we have points of intersection are where x is 0 and where x is 2. And you can see from the graph which function is on top, so we know which function to write first in our integral. Making a graph helps most people see how to set the integral up. But if you can reason it through without making the graph, if you can determine what your limits of integration are based on what your points of intersection are, and you know which function's on top, then you might be able to do a problem like this without making a graph. Before we move on, I want to go back and look at this problem again. This was the problem that we broke up into a region above the x-axis and a region below the x-axis in order to find those separate areas that we added together. We could have looked at that second integral in a slightly different way if we had recognized that y equals 0 is actually serving as a bound for that function. So we could have said that y equals 0 is the upper bound, the upper function for that part below the x-axis, and the parabola is the lower function, which means we could have written that second integral in this way. We could have said that our x-coordinates were still from 1 to 2, so we're integrating from 1 to 2, but now we can say top function is 0 minus bottom function, which is the parabola. That would give us the same value as we got before, but in this case, the value would come out to be a positive number instead of a negative, because we regarded the top function as the line and the bottom function as the parabola. Our last topic is average value of a function. So to get a little better idea of what this is all about, we're going to look at some animations. So we're going to look at this function, y equals negative x squared plus 4x. The value of a function means the number that represents the y-coordinate for any given x-coordinate. So right now, if you look at that blue point, that blue point's at 0, 0, which means when x is 0, y is 0. The value of this function is 0 when x is 0. If we move that point along the curve, let's say to a place where x is 1, then the value of the function when x is 1 is 3. So what we're really looking at here are the y-coordinates for every single x-coordinate that's on this graph. Now the average value would mean the average of all of these y-coordinates that we get when we're moving along this graph. And in this case, we're moving only from where x is 0 to where x is 4. So what's the average of all those y-coordinates? Well, you might be thinking, well, look, the highest y-coordinate's 4, so an average is what, kind of a middle point? So maybe the middle of all those y-coordinates is 2. Well, that would be a pretty good guess to think that the average y-coordinate here is 2. But it's not going to be that. And in order to see that, what we're going to do is animate this, and we're going to trace out all of the y-coordinates as we do that. So right now, our point is at 0, 0, so our value is 0. We're going to increase the x-coordinates by 1/10 all the way from 0 to 4. And we'll see what kind of points we have as we do that. Now if you'll notice, those y-coordinates are getting closer and closer and closer together. And as our x value increases to 4, then they start to get farther apart again. So now think about those red dots. They all represent points on the y-axis. If you were going to average all of those y-coordinates together of all those red dots, what do you think the average would be? Do you think it would be 2? Do you think the average of all the y-coordinates would be less than 2? Would be bigger than 2? Well, let's do a little bit of calculus and figure it out. So here's how we find average value of a function. If we have a continuous function and we're looking at some closed interval, in the case of what we were just looking at, we were looking at that function from where x is 0 to where x is 4. Then the average value, the average of all the y-coordinates of the points along that graph, is 1 over b minus a times the integral from a to b of f of x. For the function we just looked at, negative x squared plus 4x, we were looking at x-coordinates of those points that were from 0 to 4. So we want to find the integral from 0 to 4 of our function, and then multiply that times the fraction 1 over 4 minus 0, because our x-coordinates went from 0 to 4. So we'll find the antiderivative, and we'll evaluate at 0 and at 4. And remember, we have to multiply all of that times 1/4, and we end up with 2 2/3. So what we're saying is that the average y-coordinate for all of the x-coordinates along that graph is 2 2/3, which looks pretty consistent with our picture. If you look at all those red dots and think about their y-coordinates, you have a lot more dots that are greater than 2 than less than 2. So the average of all those y-coordinates, it's 2 2/3.